Hello everyone, today we'll be covering polar form of a complex number. So we've learned about the Cartesian form. Now we've learned about the Cartesian form. Now we're going to learn about the polar form. So first of all, let's take a look at this Argand diagram. We know that x plus yi gives the Cartesian form of a complex number. But we can also express a complex number in other ways. For example, over here, we can take the length of the complex number as r, and this is what we call the magnitude of a complex number. And we can also find out what theta is, which is the angle it makes with the axis over here. We call this the argument. Okay, and over here, this is r cosine theta. If we use trigonometric ratios or Tuakaso, we're able to see this. So we know that x equals to r cosine theta. As you can see over here, the real part is r cosine theta. And again, the imaginary part, or y, will just be equals to r sine theta. So you have I sine theta times r over here. So that's how the trigonometric form works. If you want to abbreviate this is just equals to r cis theta, but I won't be using this notation. Next up, the Euler or the polar form. If you look here, this is actually equal to this. The r and theta here are actually exactly the same. The magnitude for r and theta is just the argument or the angle. So the real magic of this is that cosine theta plus I sine theta is actually e to the power of I theta. And this really shows the power of Euler's number. It appears everywhere. It even has a connection to trigonometry. Okay, let's pause for a second. Let's not get too ahead of ourselves. Let's find out how to find the magnitude and argument. Again, when you're converting from the Cartesian form to the trigonometric form, what you're trying to find is this r and theta here. So r, the magnitude of the complex number, which I can write as mod of z, is just equals to square root x squared plus y squared. This is in your formula booklet. To know why this works, this is actually just using Pythagoras theorem. This is right angle over here. You have r squared equals to x squared plus y squared. Next, argument or arg z is equals to theta. Okay, wait, but there's a little bit of a caveat here. This is a pretty big caveat actually. The principal argument will be between negative pi and pi. This principal argument is a rule we try to follow when we are expressing our final answer, only our final answer. Okay, if it's our intermediate answer, it doesn't really have to follow the principal argument. And again, this is between negative pi and pi. To help you visualize this, I've drawn all 4 quadrants on an Argand diagram. Okay, look at the black complex number over here, the black one in the first quadrant. So you can see that the argument is just theta. Yeah, makes a lot of sense. Alright. And then for the second quadrant, for the purple complex number, the argument is still theta like this. Okay? Remember that when you go until here, this is where pi is, from 0 all the way to pi in terms of the angle. If you see here, the upper limit for the principal argument is pi. When it comes to the third quadrant, the argument actually has to be negative. You see here, your argument will just be negative of whatever this angle theta is over here. And similarly, for the fourth quadrant, or this green complex number, this is also a negative of this angle. So in sum, if it's in the first and second quadrant, the argument will be positive, and if it's in the third and fourth quadrant, the argument will be a negative angle. Okay, to help you find the argument, I've come up with a set of 4 different formula. Okay, this looks like a lot to remember, but it's actually not that bad. For the magnitude, this is always the formula for all 4 quadrants. It's always a positive value. But since the argument is a little bit more complicated, let's take a look. So the argument of z is equals to tangent inverse mod of y over x. Let's see why this works. The argument of z, or this angle theta, is, if we take tangent theta, this is equals to the opposite, which is y, in terms of the Cartesian form, over the adjacent, which is x. As you can see, the argument of z, which is theta in this case, is just inverse tangent of y over x. So next, for the second quadrant, arc z is just pi minus tangent inverse of y over x modulus. For the third quadrant, the argument will be actually the negative of the second quadrant. If you can tell, this is negative pi plus tangent inverse of mod y over x. And similarly, the fourth quadrant is just negative of the first quadrant, which is negative tangent inverse y over x modded. Okay? These four formula, they are not in the formula booklet by the way, can help you find the argument of any complex number pretty quickly, no matter which quadrant it is in. Next up, I know this is a lot of information to take in, but bear with me for a sec. The next thing we're going to look at is rotation. So if we look at this, if we multiply z by I, if you look over here, on the Argand diagram, this just looks like a rotation of 90 degrees anti-clockwise. And more generally, if we have any e to the power of I theta, okay, let's just say the magnitude of this is 1, it's just e to the power of I theta. If you have any e to the power of I theta times z, this will actually give a rotation of theta anti-clockwise. Okay, to see why this works, right? Let's say z has an argument of alpha, okay? So I'm taking e to the power of I theta times r e to the power of I alpha, which is what z is, right? We have r and then e to the power of I alpha. So if we simplify this, this is r e to the power of I, and then we have theta plus alpha. Because if you remember our exponent rules, when we multiply, we will just add these two together. So we get r e to the power of I theta plus alpha. And you can see that this is just r e to the power of I theta plus alpha. The total argument over here is actually theta plus alpha. Okay, and finally, utilizing the same concept, we have the modulus and argument properties. So again, earlier we kind of like multiplied two complex numbers together, right? If you have z1, z2, okay, for example, z1 is just a complex number and z2 over here is also a complex number. If you multiply these two complex numbers together, then magnitude becomes r1 times r2. This makes sense because we're just taking r1 times r2 over here. And for this, earlier remember we just added the arguments together. So over here, we're just adding the argument of z1, z2 actually just becomes theta 1 plus theta 2. Similarly, if we take z1 over z2, the magnitude just becomes r1 over r2. We're just dividing this by this. And remember what we did for the exponent, this will look something like e to the power I theta 1 divided by e to the power I theta 2. And you can tell by this that your argument will be theta 1 minus theta 2. That's why in a similar vein, what you get is theta 1 minus theta 2 as your new argument. Okay, these are really, really important, so please remember them. And finally, to the most important one. Okay, so if you have z to the power of n, let's say you have r e to the power of I theta, you want to the power of n, your magnitude will become r to the power of n, as you can see over here, r to the power of n, and then you have e to the power of I n theta. Your new argument becomes n theta, as you can see over here. Again, in case you're a little bit confused, this e to the power of I n theta is basically the same as this. I'm just converting from trigo to polar form. So again, when I take z to the power of n, I'll get r to the power of n as my new magnitude and n theta as my new argument. Okay? And over here, we actually get a really interesting result. This cosine theta plus I sine theta is basically what you call e to the power of I theta. If you take e to the power of I theta to the power of n, and this is the same as e to the power of I n theta. So if I actually use trigo form, this looks really interesting, right? Cosine theta plus I sine theta, whole thing to the power of n will be equals to cosine n theta plus I sine n theta. This is what you call De Moivre's theorem. So one application of De Moivre's theorem is actually finding out what cosine 5 theta is in terms of powers of cosine theta. What you can do over here is, let's say you take n equals to 5, and then you take the binomial expansion on the left hand side. And if you look at this, cosine 5 theta is just the real part. So you just take the real part of this left hand side. That's just one of the few applications of De Moivre's theorem. One more thing, I see my friends do this mistake all the time. If you have cosine theta to the power of 6, this is not equals to cosine 6 theta, okay? This is wrong. De Moivre's theorem only works when it's cosine theta plus I sine theta. Now we'll be moving on to the questions regarding polar form. There's going to be 3 questions, 1 simple one and 2 more complicated ones. So get ready. Okay, when we're expressing from Cartesian form in terms of polar form, we must find the magnitude, mod of z, and the argument z. So let's do that. Mod of z will just be square root of x squared plus y squared, if you remember Pythagoras theorem. So we get negative 1 square plus negative 1 square, which will just be equals to square root of 2. Our magnitude is square root of 2. For the argument, what we need to first find out is what quadrant this is going to be in. So if we draw our Argand diagram, negative 1 minus I is actually in quadrant 3. So we'll utilize this formula. Again, this is not inside the formula booklet. Please remember this. This is negative pi plus tangent inverse of mod of y over x. In this case, y is negative 1 and x is negative 1. Okay, if you're not familiar with this, tangent inverse 1 will be equals to pi over 4. If you're not familiar with this, there'll be a video that I'll be doing on special angles that I'll be doing in the trigonometry section for topic 3. So negative pi plus pi over 4 will just be negative 3 pi over 4. And that's our argument. If we want to express this in terms of polar form, what we get is negative 1 minus I equals to r, again, e to the power I theta. Theta, which is negative 3 pi over 4. And tada, we are done. Next, we want to express negative 1 minus I cubed in polar form. Let's say we have z cubed. This will be equals to r cubed cosine 3 theta plus I sine 3 theta. Okay, first I'm going to write the square root 2 to the power of 3. 2 to the power of 3 over 2. And then we have e to the power of I negative 9 pi over 4. But there's something a little bit uncanny about this. Remember your principal argument? Whenever we write arguments, right, this has to be between negative pi and pi. So actually what we need to do is find out what negative 9 pi over 4 is. So negative 9 pi over 4 is just negative 2 pi, another pi over 4. Can you see that? We're doing negative 2 pi minus pi over 4. We actually get that this, the argument of this, in terms of the principal argument, would just be negative pi over 4. So in general, if our argument doesn't come into the principal argument, we can plus minus 2k pi, where k is an integer. Okay, so we can plus 2 pi or minus 2 pi to the argument over here to help us achieve into the principal argument range. So that is negative 1 minus I to the power of cube expressed in terms of polar form. Okay, make sure to practice this. These are like the kind of like the basic level questions. The next ones will be 2 very common IB questions. Over here, it's given that z equals to 1 plus cosine theta plus I sine theta. And theta is between 0 and pi. So they want us to find what mod z and argument z is. What I want to do is express the complex number in terms of a vector. As you can see, I've kind of been alluding to this, where you express complex numbers in terms of vectors. So I see over here, 1 plus cosine theta plus I sine theta. When we have this, this is considered like the addition of 2 complex numbers. And when you have the addition of complex numbers, I like to draw an Argand diagram. So I have 1 plus cosine theta plus I sine theta, which I can write it just as e to the power of I theta. And this over here is theta. Okay, so let me draw this a little bit bigger over here. If we look at this over here, when we add the vectors, when we add 2 vectors, this is what z is. Okay, let's first find mod of z. So if you remember, mod of z is just square root of x squared plus y squared. In this case, this is x, 1 plus cosine theta. So we get 1 plus cosine theta square plus sine theta. This is your sine theta would just be your y. So you get sine theta square. And if you expand this, this will become 1 plus 2 cosine theta plus cosine square theta plus sine square theta. And if you remember, cosine square theta plus sine square theta is just equals to 1. So we'll get this as 1. And if we simplify this, this is just 2 square root of 2 plus 2 cosine theta. That is your magnitude. But if you want to simplify this a little bit further, remember that cosine 2 theta is equals to 2 cosine square theta minus 1. So we can simplify it like this. Instead of using 2 theta, we'll use theta. So this becomes theta over 2. This will be 2 times 2 cosine square theta over 2 minus 1. And let's continue. If we simplify this, this becomes square root of 4 cosine square theta over 2. After we take the square root, this becomes 2 cosine theta over 2. The next thing I want to find is the argument. Okay, so in this case, I'm going to actually take a look at the Argand diagram to help me. This yellow angle over here is pi minus theta, right? And if I want to find this, which is just the argument of z, what I'm going to do is take the 180 degrees, because this is the sum of the angles of a triangle, minus pi minus theta. So this will give us the sum of these two, and I want to divide by 2, because we know that this is an isosceles triangle. Why? Because the magnitude of e power I theta is also equals to 1. So what we get from here is that the argument is just theta over 2. Okay? Alright, the last question. Find the values of n such that square root of 3 plus I to the power of n is purely imaginary. So, purely imaginary means that there is no real part. Means that the real part will be equals to 0. First thing I want to do is convert root 3 plus I into polar form. So let's do that. To find the magnitude, I'll just take square root of x squared, which is 3, plus y squared, which is square root of 4, which is 2. Next, square root 3 plus I is actually in the first quadrant. So we can simply take that the argument of root 3 plus I is tangent inverse of y over x. In this case, we have y over x, which will be 30 degrees or pi over 6. And again, if you're not familiar with how I get pi over 6 from this, please check out the special angles in the trigonometry section. So, root 3 plus I to the power of n will be equals to 2 cosine pi over 6 plus I sine pi over 6. Oh wait, this is just root 3 plus I, so we need to do to the power of n. So if we take this to the power of n, we'll get this and this. Which again, let's use De Moivre's theorem as from earlier, and we get cosine n pi over 6 plus I sine n pi over 6. And again, purely imaginary means that the real part has to be equals to 0. So let's do that. The real part in this case is just 2 to the power n cosine n pi over 6, and we want this to be equals to 0. So this is more trigonometry, because what we want to solve is cosine n pi over 6 equals to 0. Again, if you're not familiar with this, please check out my trigo videos to help you understand a little bit better. So let's draw out the cosine graph. What we have over here is this is pi over 2. This is 3 pi over 2. I'm just marking out points where cosine will be equals to 0. So if we look at here, what values of n will get pi over 2, 3 pi over 2, such that cosine n pi over 6 will be equals to 0. So what I'll write is n pi over 6 equals to pi over 2, 3 pi over 2, 5 pi over 2. And if you look over here, this becomes actually like a kind of like an arithmetic progression where tk will just be equals to t1 plus k minus 1d. Okay, so let's figure this out. This is pi over 2 plus k minus 1, and d is also pi. Remember, this is what d is. Okay, plus pi throughout. And so what we get is pi over 2 plus k minus 1 pi. Again, where k is an integer. Again, remember that k can just be any integer, because this doesn't just have to be positive. It can be negative pi over 2 also. Alright? Okay, let me do some sort of test to test if this is correct. Let's say we get k equals to 1. Okay, we get pi over 2. If k equals to 2, we get 3 pi over 2. and then k equals to 3, we get 5 pi over 2. And if we check the negative side, we will get, if k equals to 0, we get negative pi over 2. If we get k equals to negative 1, we get negative 3 pi over 2. Okay, so this formula over here that we have is correct. Okay, if I times 6 to everything, I'll get that n pi equals to 3 pi plus 6k minus 1 pi. And if I divide everything by pi, I'll get 3 plus 6k minus 1, which will simplify to 6k minus 3. Alright, so we have solved this question. Here's a summary sheet of all the questions we've solved related to polar form. Hopefully this was useful. I know some of the questions, especially these two over here, are kind of difficult, but these two are very typical IB questions that's important to know how to do. Thank you so much for watching. I hope you enjoyed.